So here's something worth thinking about as you settle in tonight. Right now, wherever you are, energy is moving. It's flowing out of your body as warmth, radiating gently into the air around you. The pillow under your head is absorbing a tiny fraction of heat from your skin. The air in the room is doing this slow, invisible dance of molecules bumping into each other, exchanging little packets of energy, billions of collisions every second, and you can't hear any of it. You can't see it, but it's happening, constantly, everywhere, and it never stops. And the remarkable thing, the truly remarkable thing, is that for most of human history, nobody understood any of this. People could feel warmth and cold. They could light fires. They could watch ice melt in the sun. But the actual rules governing all of it, the deep laws that dictate how energy moves, why heat flows the way it does, why you can't build a machine that runs forever, why time seems to move in only one direction, those took centuries to figure out. And the story of how we figured them out is one of the best stories in all of science. That's what we're going to talk about tonight, the laws of thermodynamics. And I know that phrase alone might sound like something from a textbook you'd rather forget. But here's the thing. These aren't abstract rules that only matter in laboratories. These are the rules that govern everything. Every engine, every refrigerator, every star, every living cell in your body. The reason your coffee gets cold, the reason the universe will eventually go dark, the reason you can't unscramble an egg, all of it comes back to thermodynamics. And the people who discovered these laws, they weren't sitting in ivory towers scribbling equations. They were trying to solve real, urgent, practical problems, mostly involving steam and coal, and the question of how to get more useful work out of a machine without it exploding. Let's start where the story really begins, which is with fire. Humans have been using fire for hundreds of thousands of years. That's not an exaggeration. There's evidence of controlled fire use going back at least 300,000 years, possibly longer. And for all of that time, fire was essentially magic. Useful magic, but magic nonetheless. You put wood in a pile, you introduce a spark, and suddenly you have light, warmth, the ability to cook food, to harden clay, to keep predators away at night. But why? What was actually happening when something burned? For most of human history, the answer was some version of, the fire spirit lives in the wood, or the gods gave us flame, which is perfectly reasonable when you don't have the tools to investigate further. The ancient Greeks, as they did with so many things, took a crack at it. Aristotle and others proposed that fire was one of the 4 fundamental elements: earth, water, air, and fire. Everything in the world was supposedly made of some combination of these 4. It's a beautiful idea, honestly. Elegant. Wrong, but elegant. And it held sway for nearly 2,000 years, which tells you something about how sticky a beautiful wrong idea can be. But let's fast forward a bit, because the real action starts in the 1600s and 1700s, when people began seriously experimenting with heat and trying to understand what it actually was. And this is where you meet one of the most persistent wrong ideas in the history of science, the caloric theory. The idea was that heat was a fluid, an actual, invisible, weightless fluid called caloric that flowed from hot objects to cold ones. When you heated a piece of iron in a fire, the caloric fluid was flowing from the flames into the metal. When that hot iron cooled down in the air, the caloric was flowing back out. It was intuitive. It matched everyday experience pretty well, and some very smart people believed it for a very long time. Antoine Lavoisier, the great French chemist, the man who essentially founded modern chemistry, who figured out the role of oxygen in combustion, who gave us the law of conservation of mass. Lavoisier was a caloric believer. He actually listed caloric as one of the chemical elements in his famous 1789 textbook. Think about that. One of the most brilliant scientific minds in history, a man who got so many things right, and he was convinced that heat was a substance you could pour from one thing to another like water. He even had logical reasons for it. When you add heat to ice, it melts. It seemed like the caloric fluid was getting between the ice particles and pushing them apart, turning solid into liquid. Add more caloric, and the liquid becomes gas. It all made a kind of sense. Lavoisier's story, by the way, has one of the most tragic endings in the history of science. During the French Revolution, he was arrested, partly because of his involvement with the Ferme Générale, the much-hated tax collection agency. He was tried, convicted, and guillotined in 1794. He was 50 years old. The mathematician Joseph Louis Lagrange reportedly said the next day, "It took them only an instant to cut off his head, and 100 years might not suffice to reproduce its like. A devastating loss. But the caloric theory survived him." Now, the first serious cracks in the caloric theory came from an unlikely source, a man named Benjamin Thompson, who later became Count Rumford. And his story is fascinating. Thompson was born in 1753 in Woburn, Massachusetts, so he was an American colonist. During the Revolutionary War, he sided with the British, which made him deeply unpopular in his home country. He eventually fled to Europe, where he had an extraordinary second career. He ended up in Bavaria, working for the Elector, and he was put in charge of, among other things, the military arsenal in Munich. And it was there, around 1798, that he made an observation that would quietly begin to unravel the caloric theory. He was overseeing the boring of cannon barrels, literally drilling out the inside of brass cylinders to make cannons. And he noticed something that bothered him. The process generated an enormous amount of heat. The metal shavings were hot. The cannon barrel was hot. The boring tool was hot. Everything was hot. And the heat seemed to be inexhaustible. As long as you kept drilling, heat kept coming. Now, if heat were a fluid, if caloric were a real substance contained within the metal, you'd expect it to eventually run out. You can only squeeze so much water out of a sponge. But the heat from boring just kept coming and coming, as long as the horses kept turning the drill. Thompson did careful experiments. He even immersed the cannon barrel in water and measured how long it took to bring the water to a boil just from the friction of boring. And his conclusion was radical for the time. Heat was not a substance. Heat was motion. The mechanical work of the drill was being converted into heat. The friction was causing the particles of the metal to vibrate faster, and that vibration was what we experience as heat. He published his findings, and people mostly ignored him, or argued with him. The caloric theory was too entrenched, too useful, too elegant. Thompson was seen as a bit of an outsider, a self-promoter, which, honestly, he kind of was. He had a complicated personality. But he was right. He was absolutely right. And it would take another 50 years for the scientific establishment to fully come around. Here's what's interesting about that delay, though. It wasn't just stubbornness. The caloric theory actually worked pretty well for a lot of practical calculations. If you treated heat as a fluid that flowed from hot to cold, you could make accurate predictions about how fast things would cool down, how much heat you needed to raise the temperature of a given amount of water, all sorts of useful stuff. A wrong theory can still be a useful theory, and that's a lesson that shows up again and again in the history of science. Newtonian gravity is wrong. Einstein showed us that. But it's still good enough to land a spacecraft on the moon. The caloric theory was wrong about what heat fundamentally was, but it was good enough for many engineering purposes, and that made it hard to kill. But while the philosophers and chemists were arguing about the nature of heat, something else was happening, something much more practical, much more urgent, and ultimately much more consequential. People were building engines, steam engines specifically. And the story of thermodynamics is inseparable from the story of steam, because it was the desperate need to make steam engines more efficient that drove people to discover the actual laws governing energy and heat. Now, you probably know the basic story: James Watt and the steam engine. But the real history is richer and messier than the simple version. Steam power didn't start with Watt. It started with a man named Thomas Savery, who in 1698 patented a device he called the miner's friend, a steam-powered pump designed to remove water from coal mines. Flooding was a constant, deadly problem in mines. As shafts went deeper, water seeped in, and you needed some way to pump it out. Savery's device used steam pressure to push water up through pipes. It sort of worked, but it was limited and dangerous. The boilers had a tendency to explode, which is not ideal. Then came Thomas Newcomen, who by 1712 had built something much more practical: the atmospheric engine. And this is a beautiful piece of engineering to think about. Here's how it worked. You had a large cylinder with a piston inside. Steam from a boiler would fill the cylinder, pushing the piston up. Then you'd spray cold water into the cylinder, which would condense the steam, creating a partial vacuum. And now, atmospheric pressure, the weight of the air above, would push the piston back down. That downward stroke was connected to a rocking beam, and the other end of the beam was connected to a pump rod that went down into the mine. Piston goes up, pump rod goes down. Piston goes down, pump rod goes up, pulling water with it. Back and forth, all day long. It was slow. It was massive. These engines were the size of buildings, and it was fantastically inefficient. Something like 99% of the energy in the coal was being wasted. But it worked. It pumped water out of mines that would otherwise have been unusable. And it spread across Britain's mining districts throughout the 1700s, this clanking, hissing, coal-devouring giant that kept the mines dry and the coal flowing. And here's where James Watt enters the picture, and the story is genuinely wonderful. Watt was an instrument maker at the University of Glasgow. He made and repaired scientific instruments. In 1763 or so, he was asked to repair a small model of a Newcomen engine that the university used for demonstrations. And as he worked on it, he became obsessed with the question: why was it so inefficient? Why did it burn so much coal for so little useful work? He realized the fundamental problem. In the Newcomen engine, you were heating the cylinder with steam and then cooling it with water in the same vessel over and over. Every cycle, you had to reheat the cylinder walls that you just cooled down. All that energy spent reheating the cylinder was pure waste. It was like trying to cook dinner by heating your oven to 400 degrees, then cooling it to room temperature, then heating it again for every single dish. Watt's insight, and this came to him during a walk on Glasgow Green on a Sunday afternoon in 1765, or so the story goes, was to use a separate condenser. Keep the main cylinder hot all the time. When you need to condense the steam, don't spray cold water into the cylinder. Instead, open a valve and let the steam flow into a separate chamber, the condenser, which is kept cold. The cylinder stays hot, the condenser stays cold, and you stop wasting all that energy on reheating. It sounds simple when you say it like that, but it was revolutionary. It roughly tripled the fuel efficiency of the steam engine, and it made Watt famous and eventually wealthy through his partnership with the Birmingham manufacturer Matthew Boulton. By the 1780s and 1790s, Boulton and Watt engines were powering not just mine pumps, but factories, mills, breweries. The entire industrial revolution was being driven, quite literally, by this improved understanding of how to manage heat and work. But here's what's fascinating. Watt made the engine dramatically better through practical insight and careful engineering. What he didn't have, what nobody had yet, was a theoretical framework for understanding why his improvement worked. There was no science of thermodynamics. There were no laws. There was no clear understanding of the relationship between heat and work. No concept of energy as we understand it today. Watt was an engineer, not a physicist, and he solved his problem the way great engineers do, through observation, intuition, and relentless experimentation. The theory would come later, and it would come from a place you might not expect, not from the workshops of Britain, where the engines were actually being built, but from the study of a young French military engineer who never built an engine in his life. His name was Sadi Carnot, and he was about to ask a question so profound that it would lay the foundation for the entire science of thermodynamics. He was going to ask, what is the absolute maximum efficiency that any heat engine can ever achieve? Not a specific engine. Any engine. Is there a fundamental limit built into the laws of nature themselves? And the answer he found would change everything. But to understand how he got there, you need to know a little bit about who he was and the world he grew up in. Sadi Carnot was born in 1796, right in the middle of revolutionary France. His father was Lazare Carnot, and that name matters. Lazare was a mathematician, a military strategist, and one of the most powerful political figures in France during the Revolution and the Napoleonic era. He was sometimes called the organizer of victory because he essentially rebuilt the French army's logistics and strategy during the Revolutionary Wars. So Sadi didn't come from nowhere. He grew up in a household where intellectual rigor and strategic thinking were just the air you breathed. His father had actually done serious work on the mechanics of machines. He'd written about the efficiency of water wheels and mechanical systems, asking questions about how much useful work you could extract from a given input. So when young Sadi eventually turned his attention to heat engines, he was, in a way, continuing a family tradition. He just took it somewhere his father never imagined. Sadi studied at the École Polytechnique in Paris, which was at the time probably the finest technical school in the world. He graduated, served briefly as a military engineer, and then found himself on half pay with not much to do. This was after Napoleon's fall, and France was in a strange period, politically unstable, economically uncertain, and deeply aware that it was falling behind Britain industrially. And that last point really bothered Carnot. He could see that Britain's industrial dominance was built on the steam engine. British engines were pumping mines, driving factories, powering ships. And France was importing British technology, or trying to copy it, without really understanding the principles behind it. Carnot wanted to change that, not by building a better engine. He wasn't that kind of engineer. But by understanding, at the deepest possible level, what made any engine work. What were the fundamental principles governing the conversion of heat into motion? And here's the thing that makes Carnot's work so remarkable. He was still working within the caloric theory. Remember, This was the idea that heat was a fluid, an invisible substance called caloric that flowed from hot bodies to cold ones. We talked about how Count Rumford had challenged this idea back in 1798 with his cannon boring experiments, suggesting that heat was actually a form of motion. But Rumford's ideas hadn't really taken hold yet, especially in France. The caloric theory was still the dominant framework. So Carnot was building his theory on a foundation that was, strictly speaking, wrong. And yet, and this is what's so beautiful about it, the conclusions he reached were absolutely correct. His reasoning was so clean, so elegant, that it transcended the flawed assumptions underneath it. In 1824, when he was just 28 years old, Carnot published a slim book called Reflections on the Motive Power of Fire. It's not a long work. It's maybe 100 and some pages, and it was almost completely ignored when it came out. Hardly anyone read it. It sold poorly. Carnot himself died just 8 years later, in 1832, during a cholera epidemic in Paris. He was 36. Most of his papers were burned after his death, as was common practice during cholera outbreaks to prevent the spread of disease. So here's this work of genuine genius, one of the most important scientific publications of the 19th century, and it nearly vanished from history entirely. But let's talk about what was actually in it, because it's gorgeous in its simplicity. Carnot's key insight came from an analogy. He compared a heat engine to a water wheel. Think about how a water wheel works. Water falls from a higher elevation to a lower elevation, and as it falls, it turns the wheel, which does useful work. Grinding grain, running a saw, whatever you need. The amount of work you can extract depends on two things: how much water there is and how far it falls. The greater the height difference, the more work you get. Now, Carnot said, a heat engine works the same way, except instead of water falling from a height, you have heat, caloric in his framework, falling from a high temperature to a low temperature. The engine sits between the hot source and the cold sink, and it extracts work as the heat flows through it, just like the water wheel extracts work as water flows through it. This analogy is so intuitive, so visual, that you can almost feel it. The hot source is like a reservoir up on a hill. The cold sink is like the pond at the bottom. The engine is the wheel in between. And the crucial insight is this: the amount of work you can possibly extract depends on the temperature difference. The bigger the gap between your hot source and your cold sink, the more work you can get. Makes sense, right? If the water only falls a few inches, the wheel barely turns. If it falls 100 feet, you've got real power. But Carnot went further. He asked, what would a perfect engine look like? An engine that wastes absolutely nothing? And he described what we now call a Carnot engine. An idealized, theoretical engine that operates through a specific cycle of steps. It's not a real machine. Nobody can actually build one. It's a thought experiment, a mental model. But it sets the absolute upper limit on efficiency. Here's how it works, at least conceptually. You have a gas, let's say air, trapped in a cylinder with a piston. First, you let the gas expand slowly while it's in contact with the hot source, absorbing heat and pushing the piston out. This is an isothermal expansion. The temperature stays constant because heat is flowing in from the source. Then you insulate the cylinder, cut it off from both the hot source and the cold sink, and let the gas continue expanding. Now it cools as it expands because it's doing work but not receiving any heat. This is an adiabatic expansion. Then you bring the cylinder into contact with the cold sink and slowly compress the gas pushing heat out into the cold reservoir. Isothermal compression. And finally, you insulate it again and compress it a little more, raising its temperature back to the starting point. Adiabatic compression. And now you're back where you started. One complete cycle. The gas has returned to its original state, and along the way, you've extracted some network. The piston pushed out more during the expansion phases than you had to push it in during the compression phases. Now, if you're drifting a little, that's totally fine. The details of the cycle matter less than the big idea, which is this. Carnot showed that even this perfect, idealized engine, an engine with no friction, no heat leaks, no wasted anything, still cannot convert all of the heat into work. Some heat must always be rejected to the cold sink. Always. That's not an engineering limitation. It's not something you can fix with better materials or tighter seals. It's a fundamental feature of how the universe works. You cannot convert heat entirely into work. Some of it always has to flow through to the cold side. And here's the kicker. Carnot calculated the maximum efficiency of this ideal engine, and it depends only on the temperatures of the hot source and the cold sink. Nothing else. Not the type of gas, not the size of the cylinder, not the material it's made of. Just the two temperatures. The formula, expressed in modern terms, is beautifully simple. The efficiency equals 1 minus the ratio of the cold temperature to the hot temperature, where both temperatures are measured on an absolute scale, what we now call Kelvin. So if your hot source is at 600 Kelvin and your cold sink is at 300 Kelvin, the maximum possible efficiency is 1 minus 300 over 600, which is 1/2 or 50%. That's the ceiling. No engine operating between those two temperatures can ever do better than 50%, no matter how cleverly it's designed. Think about what that means for a second. It means there's a law of nature that puts a hard cap on how much useful work you can extract from heat. And it means that the only way to improve your maximum efficiency is to either raise the temperature of your hot source or lower the temperature of your cold sink. That's it. Those are your only levers. And since your cold sink is usually the surrounding environment, the air, a river, the ocean, you can't really make it much colder. So in practice, the path to better engines has always been the same. Make things hotter. Higher steam temperatures, higher pressures, hotter combustion. The entire history of engine development, from Watt's day to modern gas turbines, has been a relentless push toward higher operating temperatures, and Carnot's work tells you exactly why. Now remember, almost nobody read this when it came out. Carnot died young, his papers were burned, and for about a decade, his ideas were essentially lost. But there was one person who noticed. A French engineer named Émile Clapeyron read Carnot's book and, in 1834, published a paper that restated Carnot's ideas in a more mathematical form, with proper equations and the famous pressure-volume diagrams that engineering students still use today. Clapeyron's paper was more accessible, more formal, and it slowly began to circulate. It reached Germany. It reached Britain. And it eventually landed in the hands of two men who would take Carnot's insights and build them into the full edifice of thermodynamics. One of them was a German physicist named Rudolf Clausius. The other was a Scottish-Irish physicist named William Thomson, who would later become Lord Kelvin. Yes, the same Kelvin whose name is on that absolute temperature scale. These two men, working somewhat independently, somewhat in dialogue with each other, would formalize the first and second laws of thermodynamics in the 1850s. But to understand how they got there, you need to know about a detour, a crucial piece of the puzzle that was being worked out at almost the same time in a completely different context. Because while Carnot was thinking about engines in France, a quiet, self-taught brewer's son in the north of England was about to prove something that would shake the foundations of physics. He was going to show, through painstaking experiment, that heat and mechanical work are interchangeable, that they are, in fact, different forms of the same thing. His name was James Prescott Joule, and his story begins in a brewery in Salford, just outside Manchester, in the early 1840s. Joule was born in 1818, the son of Benjamin Joule, who owned a successful brewery. And that brewery matters more than you might think, because it shaped everything about how James approached science. See, brewing is a business that depends on temperature. You need to control fermentation. You need to understand how heat moves through liquids. You need to measure things precisely, or you lose money. So James grew up in an environment where careful measurement wasn't abstract. It was practical. It was economic. It was the difference between a good batch and a ruined one. He was a sickly child, educated mostly at home and by private tutors. And here's a wonderful detail. For a while, his tutor was none other than John Dalton, the great chemist and physicist who gave us modern atomic theory. Imagine that. You're a teenager in Manchester, and the person teaching you science is one of the most important chemists in history. Dalton instilled in Joule a deep respect for precise measurement, for letting the data speak, for not assuming you know the answer before you've done the experiment. That training would define Joule's entire career. Now, Joule wasn't a university professor. He didn't have a position at Cambridge or Oxford. He was a brewer who did science in his spare time, using equipment he built or modified himself, often in rooms adjacent to the brewery. And the scientific establishment of the time could be quite snobbish about that. When Joule first started presenting his results, a lot of people didn't take him seriously. He was an amateur, a provincial, a tradesman's son. But here's the thing. His experiments were extraordinary, not because they were flashy or dramatic, but because they were unbelievably precise for their time. What Joule set out to do, starting in the early 1840s, was measure the relationship between mechanical work and heat. And to understand why this was so radical, you need to remember where the scientific consensus stood. Most physicists still believed in some version of the caloric theory, the idea that heat was a fluid, a substance, something that was conserved. It could flow from hot to cold, but it couldn't be created or destroyed. Carnot himself had worked within that framework. If caloric theory was right, then heat and mechanical work were fundamentally different things. You couldn't convert one into the other any more than you could convert water into iron. But Joule suspected otherwise. He'd been doing experiments with electric currents. Remember, this is also the era when electromagnetism is being figured out. And he'd noticed something. When you run an electric current through a wire, the wire gets hot. And the amount of heat produced was proportional to the square of the current times the resistance. We call this Joule heating today. And it's why your phone charger gets warm, why toasters glow red, why electric heaters work. Joule published this relationship in 1841, when he was just 22 years old, and it nagged at him, because if you could convert electrical energy into heat, and you could generate electrical energy from mechanical motion using a dynamo, say, then couldn't you, in principle, convert mechanical work directly into heat? And if you could, then heat wasn't a substance at all. It was a form of energy. So he designed what became one of the most famous experiments in the history of physics. You've probably heard of it, the paddle wheel experiment. Picture this. You have an insulated container of water. Inside the water, there's a set of paddle wheels, like little fans. These paddles are connected by a string and pulley system to a falling weight. When the weight drops, it turns the paddles. The paddles churn the water, and churning water, creating friction and turbulence in a liquid, should, if Joule was right, raise the temperature of the water by a measurable amount. Now think about what he's measuring here. He's measuring how much the temperature of the water goes up when a known weight falls through a known distance. The falling weight does a precise amount of mechanical work. You can calculate it exactly from the mass and the height. And the temperature rise tells you how much heat was generated. If there's a consistent ratio between the work done and the heat produced, then you've proven that mechanical work and heat are interchangeable, and you've measured the conversion factor. The problem is that the temperature changes are tiny. We're talking about fractions of a degree Fahrenheit. To measure that in the 1840s, with the thermometers available, required almost superhuman patience and care. Joule had his thermometers custom made. He calibrated them obsessively. He accounted for heat loss to the surroundings, for the heat absorbed by the container itself, for air resistance on the falling weights, for every possible source of error he could think of. He ran the experiment over and over and over. And here's what he found. There was a consistent ratio. Every time, roughly the same amount of mechanical work produced roughly the same amount of heat. He called this the mechanical equivalent of heat. In modern units, his best measurements came out to about 4.16 joules per calorie, remarkably close to the accepted modern value of 4.186 joules per calorie. For a self-taught brewer working in a room next to a brewery in northern England, that is astonishing accuracy. But when he first presented these results, in 1843, and then more fully in 1845, the reception was lukewarm at best. He read a paper to the British Association for the Advancement of Science, and it was met with polite indifference. Nobody attacked him. They just didn't seem to grasp the significance. Part of the problem was that Joule was claiming something enormous. He was saying that the caloric theory was wrong, that heat was not a substance, that energy could change forms. That's a big claim from a young brewer nobody had heard of. But Joule kept at it. He tried different methods: electrical heating, compressing gases, forcing water through narrow tubes, and every method gave him the same ratio. The mechanical equivalent of heat was a real, consistent, measurable number, and gradually people started to notice. The turning point came in 1847, at a meeting of the British Association in Oxford. Joule gave another presentation, and this time, a young Scottish-Irish physicist in the audience was paying very close attention. That physicist was William Thomson, 23 years old, already a professor at the University of Glasgow, brilliant, ambitious, and deeply interested in heat. Thomson had been studying Carnot's work through Clapeyron's paper, and he was troubled. Carnot's theory seemed to require that heat was conserved, that it flowed through an engine, like water through a water wheel, doing work but not being used up. But Joule was saying heat could be created from scratch by doing mechanical work. Both couldn't be right. Could they? Thomson was initially skeptical of Joule, but he was also honest enough to recognize that Joule's experiments were meticulous, and his results were consistent. The two men struck up a correspondence, and then a friendship, that would last decades. And Thomson began the difficult intellectual work of reconciling Carnot's insights about engine efficiency with Joule's proof that heat and work were interchangeable. This is one of those beautiful moments in the history of science where two seemingly contradictory ideas turn out to both be partially right, and the resolution creates something deeper than either one alone. Carnot was right that you need a temperature difference to extract work, and that there's a maximum efficiency for any heat engine. But he was wrong that heat is conserved, that the same amount of heat flows out the cold side as flows in the hot side. Joule was right that heat and work are interchangeable, that energy is conserved in the broader sense. The resolution is the first law of thermodynamics, the conservation of energy, combined with the second law, which tells you about the directionality and the limits. But Thomson wasn't the only one working on this puzzle. Across the North Sea in Germany, Rudolf Clausius was thinking along very similar lines. Clausius was a different kind of thinker from Joule, theoretical, mathematical, systematic. Born in 1822 in Köslin, Prussia, that's now Koszalin, Poland, he studied at the University of Berlin and was steeped in the German tradition of mathematical physics. In 1850, Clausius published a landmark paper that essentially stated both the first and second laws of thermodynamics in a clear, rigorous form. He argued that energy is conserved, that the total energy in any process remains constant, just changing forms, and separately, that heat cannot spontaneously flow from a cold body to a hot body. That second statement might sound obvious, but think about what it really means. It's not just saying that hot things warm up cold things. It's saying there's a fundamental directionality to heat flow, a one-wayness that can't be reversed without doing work. Your refrigerator moves heat from cold to hot, but only because you're pumping energy into it through the compressor. Left to its own devices, heat always flows downhill, from hot to cold, never the other way. Clausius was careful and precise in his reasoning, and he gave credit to Carnot while also correcting Carnot's error about caloric conservation. He showed that in a heat engine, some of the heat from the hot source is indeed converted into work. It doesn't all flow through to the cold side, but you can never convert all of it. Some heat must always be rejected to the cold reservoir. That's the price of the second law, and the amount you must reject depends on those temperatures, exactly as Carnot had intuited. Now, Thomson, who by this point was becoming Lord Kelvin, though the title came a bit later, arrived at very similar conclusions around the same time, though he framed the second law slightly differently. Thomson's version focused on the impossibility of a perfect heat engine. You cannot, he said, build a device that operates in a cycle and does nothing except convert heat from a single source entirely into work. There must always be waste heat. Always. This is sometimes called the Kelvin-Planck statement of the second law, and it sounds like a limitation, which it is, but it's also something deeper. It's telling you something fundamental about the nature of the universe, that perfect efficiency is not just practically difficult, it's theoretically impossible. And here's what's remarkable. Clausius's version and Thomson's version, though they sound different, are logically equivalent. If you could violate one, you could violate the other. They're two faces of the same deep truth. And that truth, the second law, is arguably the most important law in all of physics. Not because it's the most precise or the most mathematical, but because it governs everything. It governs why time seems to move in one direction, why you can't unscramble an egg, why perpetual motion machines don't work, why stars eventually burn out. But in the early 1850s, all of this was still being sorted out. The vocabulary wasn't settled, the concepts were still being sharpened, and there was a crucial idea missing, a concept that would tie the second law together and give it quantitative teeth. Clausius sensed it. He knew that the second law was about more than just heat flow. It was about something being lost, or rather, something being gained. Some quantity that always increases in natural processes. some measure of the universe's inexorable slide toward a particular kind of equilibrium. He spent years thinking about this, refining his mathematics, working through example after example. And in 1865, he finally gave this quantity a name. He chose it deliberately, picking a word that would echo energy, but mean something quite different. He called it entropy. He called it entropy. And the word itself is worth lingering on for a moment, because Clausius was very deliberate about it. He constructed it from the Greek word trope, meaning transformation or turning. He wanted it to sound like energy, deliberately, so that the two concepts would sit side by side in the mind, partners in describing how the universe works. Energy tells you what's conserved. Entropy tells you what's changing. Energy tells you the total. Entropy tells you the direction. And that direction, Clausius said, is always the same. In any real process, any process that actually happens in nature, the total entropy of the universe either stays the same or increases. It never decreases. Never. That's the second law, stated in its most compact and powerful form, and Clausius summarized the two laws of thermodynamics in a pair of sentences that are still quoted today, sentences that are almost poetic in their simplicity. He wrote, "The energy of the universe is constant. The entropy of the universe tends to a maximum." Think about that for a second. Two sentences. One says nothing is ever created or destroyed. The total amount of energy in the cosmos is fixed, was fixed at the beginning, will be fixed at the end. The other says that despite this conservation, something is always happening. Something is always shifting, always spreading out, always moving toward a state of greater disorder, greater equilibrium, greater entropy. The universe isn't running down in the sense of losing energy. It's running down in the sense of losing useful energy. The total stays the same, but the quality degrades. And that degradation is entropy. Now, this is one of those ideas that sounds simple when you first hear it, and then the more you think about it, the more profound and strange it becomes. So let's sit with it for a while. Let's really try to feel what entropy means, because it's one of those concepts that people throw around. Entropy increases. Everything tends toward disorder. But the actual mechanics of it, the actual engineering reality of it, is richer and more interesting than the bumper sticker version. Here's one way to think about it. Imagine you have a hot cup of coffee sitting on your kitchen counter. The coffee is hot. The room is cool. What happens? You already know. The coffee cools down. Heat flows from the coffee into the surrounding air. The coffee loses thermal energy. The air gains it. Total energy? Conserved. Nothing lost. But something has changed. Before, you had a concentration of thermal energy, a hot thing in a cool room. That concentration was useful. You could, in principle, have used that temperature difference to do work, run a tiny heat engine between the hot coffee and the cool air. But after the coffee cools to room temperature, that opportunity is gone. The energy is still there. It's in the air now, spread out, diffuse. But it's useless. You can't extract work from a uniform temperature. The entropy of the system has increased. The energy has spread out, become less concentrated, less available for doing anything interesting. And here's the thing. This process is irreversible. The coffee doesn't spontaneously reheat itself by pulling energy back from the room air. It could, in principle, without violating conservation of energy. The total energy would still balance, but it doesn't happen because it would violate the second law. It would decrease entropy, and the universe doesn't do that on its own. This is what makes the second law so different from the first. The first law is like an accountant. It tracks the books, makes sure everything adds up. The second, law is like a one-way street sign. It tells you which direction processes actually go. And that's what Clausius captured with entropy. He gave the one-way street a number. Now, the mathematical definition Clausius used is worth understanding, at least in broad strokes. For a reversible process, an idealized, infinitely slow process where everything stays in perfect equilibrium, the change in entropy is defined as the heat transferred divided by the temperature at which the transfer happens. Heat in divided by temperature. That's the infinitesimal change in entropy. And for a complete cycle, like Carnot's ideal cycle, the total change in entropy is zero. Everything balances perfectly. But for any real process, any irreversible process, the entropy change is greater than what you'd calculate from the heat transfer alone. There's always extra entropy generated. Always. That extra entropy is the tax the universe charges for anything real happening. And this connects back beautifully to what Carnot figured out decades earlier, even though Carnot never knew the word entropy. Remember, Carnot showed that the maximum efficiency of a heat engine depends only on the temperatures of the hot source and cold sink. 1 minus the ratio of cold to hot. What Clausius showed is that this limit exists precisely because of entropy. A perfectly reversible engine, Carnot's ideal, produces no extra entropy. It's the most efficient possible because it wastes nothing to irreversibility. Every real engine falls short because real processes generate entropy, friction, turbulence, heat leaking through finite temperature differences, gases expanding too fast to stay in equilibrium. All of these things create entropy, and every bit of entropy created is efficiency lost. So entropy isn't just an abstract philosophical concept, it's an engineering reality. It's the reason your car engine converts only about 20 to 25% of the fuel's energy into motion. It's the reason power plants, even modern ones, throw away enormous amounts of heat into cooling towers and rivers. It's the reason engineers spend careers trying to minimize irreversibilities in turbines, compressors, heat exchangers, because every irreversibility is entropy generated, and every bit of entropy generated is energy you can't use. Let's talk about what happened after Clausius, because the story doesn't stop with naming entropy. In fact, naming it was almost like opening a door into a room full of new questions. One of the biggest was this: what is entropy, really? Clausius defined it mathematically in terms of heat and temperature, but what does it mean physically? What's actually happening at the level of atoms and molecules when entropy increases? This is where Ludwig Boltzmann enters the story. And honestly, Boltzmann's story is one of the most dramatic and heartbreaking in all of science. He was born in Vienna in 1844, grew up in the Austrian Empire during a period of tremendous intellectual ferment, and became one of the most brilliant physicists of the 19th century. But his ideas were controversial, fiercely, bitterly controversial. And the opposition he faced contributed to a personal tragedy that still echoes through the history of physics. Here's what Boltzmann did. He took the concept of entropy, which Clausius had defined in terms of bulk properties, heat, temperature, macroscopic measurements, and he connected it to the microscopic world, to atoms, to molecules, to the statistical behavior of unimaginably large numbers of tiny particles. Now, you have to understand, in the 1870s and 1880s, the very existence of atoms was still debated. Seriously. There were prominent physicists and chemists, Ernst Mach, Wilhelm Ostwald, among others, who argued that atoms were a useful fiction, a mathematical convenience, not real physical entities. They believed that thermodynamics should be formulated purely in terms of energy and macroscopic quantities, without any reference to invisible particles that no one had ever directly observed. And Boltzmann was on the other side of this debate, passionately, stubbornly, brilliantly insisting that atoms were real and that the behavior of matter could be understood by analyzing the statistical mechanics of vast collections of particles. His key insight, and this is genuinely one of the most beautiful ideas in all of physics, was that entropy is a measure of the number of microscopic arrangements that correspond to a given macroscopic state. Let me unpack that, because it's worth really understanding. Think about a box of gas. You can describe the gas macroscopically: its temperature, its pressure, its volume. Those are the things you can measure with thermometers and pressure gauges. But microscopically, that same gas is made up of billions upon billions of molecules, each one zipping around with its own position and velocity. Now, here's the key question. How many different ways could those molecules be arranged, different positions, different velocities, and still give you the same macroscopic temperature, pressure, and volume? That number, the number of possible microscopic arrangements consistent with the macroscopic state, is what Boltzmann connected to entropy. A state with high entropy is one that can be realized in an enormous number of microscopic ways. A state with low entropy can only be realized in relatively few ways. And since molecules are constantly bouncing around, constantly rearranging themselves randomly, the system naturally tends toward the state that has the most possible arrangements, the highest entropy state. Not because there's some force pushing it there, but simply because there are overwhelmingly more ways to be in that state than in any other. Think about it like shuffling a deck of cards. There's only one arrangement that gives you all the cards in perfect order, ace through king, suit by suit. But there are astronomical numbers of arrangements that look like random shuffles, so if you keep shuffling, you'll essentially never land on perfect order by chance. The deck naturally tends toward disorder, not because disorder is being imposed, but because disorder is overwhelmingly more probable. That's entropy. That's the second law. It's not a law of force, it's a law of probability. And Boltzmann captured this with an equation that is now carved on his tombstone in Vienna. S equals K log W. Entropy equals Boltzmann's constant times the natural logarithm of W, where W is the number of microscopic arrangements, the number of microstates, corresponding to the macroscopic state. It's arguably the most important equation in statistical mechanics, and it bridges the gap between the world of individual atoms and the world of steam engines and thermometers. It says that the macroscopic quantity Clausius defined, entropy, has a microscopic meaning. It's about counting possibilities. It's about probability. And here's what's really clever about this. It explains why the second law works the way it does without requiring any special force or mystical tendency. It's pure statistics. When you have a system with 10 to the 23rd particles, that's roughly the number of molecules in a breath of air, the probability of spontaneously moving to a lower entropy state is so absurdly, incomprehensibly small that it effectively never happens. It's not impossible in the strict mathematical sense. It's just so unlikely that you'd have to wait longer than the age of the universe, vastly longer, to see it happen even once. So for all practical purposes, entropy always increases. The second law is a statistical certainty. not an absolute logical necessity, but the statistics are so overwhelming that the distinction doesn't matter for anything in the real world. But this statistical interpretation was exactly what made Boltzmann's contemporaries uncomfortable. Mach and Ostwald and others attacked him relentlessly. They didn't believe in atoms, so the whole foundation of his argument seemed like fantasy to them. The debates were public, heated, sometimes personal. Boltzmann felt increasingly isolated, increasingly frustrated that his life's work was being dismissed by people he respected. He suffered from what appears to have been severe depression, possibly bipolar disorder, and in 1906, while on vacation with his family near Trieste, he took his own life. He was 62 years old. The tragedy is compounded by timing. Just a few years later, the evidence for atoms became overwhelming and undeniable. Einstein's 1905 paper on Brownian motion, the random jittering of tiny particles suspended in liquid, provided a theoretical framework that was soon confirmed experimentally by Jean Perrin. Atoms were real. Boltzmann had been right all along, and his statistical interpretation of entropy became the foundation of an entire branch of physics, statistical mechanics, that underpins everything from materials science to chemistry to modern computing. His equation, S equals K log W, carved into that tombstone in Vienna's central cemetery, stands as one of the most concise and profound statements in all of science. And if you ever visit Vienna and find yourself wandering through that cemetery, past the graves of Beethoven and Brahms and Schubert, you'll find Boltzmann's grave there too, with that equation looking out at you, quiet and permanent. But the story of entropy doesn't end with Boltzmann's statistical interpretation, because the concept kept evolving, kept finding new applications, kept revealing new depths. And one of the most fascinating extensions came from an entirely unexpected direction, not from physics, not from engineering, but from information theory. In the late 1940s, a brilliant engineer at Bell Labs named Claude Shannon was working on a completely different problem, the problem of how to transmit messages efficiently over noisy communication channels. And in the course of solving that problem, Shannon discovered something remarkable. The mathematics of information looked exactly like the mathematics of entropy. Shannon's key quantity, the measure of how much information a message contains, or equivalently how much uncertainty you have before receiving it, turned out to follow the exact same mathematical form as Boltzmann's entropy. And when Shannon was deciding what to call this quantity, the story goes that he asked the great mathematician John von Neumann for advice. Von Neumann reportedly told him, "Call it entropy. In the first place, the mathematical formula is the same as in thermodynamics, and in the second place, nobody really knows what entropy is, so in a debate, you will always have the advantage." Now, whether that conversation happened exactly that way is a matter of some debate. It's one of those anecdotes that gets passed around so much it becomes hard to verify. But the mathematical connection Shannon uncovered was absolutely real and absolutely profound. Think about what Shannon was doing. He was trying to figure out the fundamental limits of communication. If you want to send a message through a wire, or through the air, or through any channel that might introduce errors, what's the most efficient way to encode that message? How much can you compress it before you start losing meaning? And how do you protect it against noise? Shannon published his landmark paper, A Mathematical Theory of Communication, in 1948, and it essentially created the field of information theory overnight. And right there in the mathematics was this quantity that measured the information content of a message source, and it had the same logarithmic structure as Boltzmann's entropy. For a set of possible messages, each with some probability of occurring, Shannon's information entropy is the sum of each probability times the logarithm of that probability, with a minus sign out front to make it positive. If you squint at that, it's Boltzmann's formula in different clothes. Here's what's really beautiful about this. Think about a coin flip. If the coin is fair, 50-50, You have maximum uncertainty about the outcome before the flip. That flip carries one full bit of information. Shannon's entropy is at its maximum. But if the coin is rigged, say 99% heads, you already pretty much know what's going to happen. There's very little surprise, very little information in the outcome. Shannon's entropy is low, so information, in Shannon's framework, is fundamentally about surprise, about the unexpected, and that maps onto thermodynamic entropy in a deep way. A gas that's spread evenly throughout a box is in its highest entropy state. There's maximum uncertainty about where any given molecule is. All the microstates are roughly equally likely. A gas crammed into one corner is low entropy. You know a lot about where the molecules are. Less uncertainty. Less surprise. This connection between entropy and information has become one of the most fertile ideas in modern science. It shows up in black hole physics, where Stephen Hawking and Jacob Bekenstein showed that a black hole has an entropy proportional to its surface area, and that entropy is essentially a measure of how much information the black hole has swallowed. It shows up in biology, in understanding how DNA encodes information. It shows up in cryptography, in data compression, in machine learning. Every time you stream a video or make a phone call, Shannon's information entropy is working behind the scenes, governing how your data gets compressed and transmitted and error corrected. But let's not get too far ahead of ourselves. Let's come back to the main thread of thermodynamics, because there's a whole other law we haven't really talked about yet, and it's the one that completes the picture in a way that's both elegant and a little bit strange. I'm talking about the third law of thermodynamics. So we've got the first law, energy is conserved. We've got the second law, entropy tends to increase. The third law is about what happens at the very bottom of the temperature scale, what happens as you approach absolute zero. The story of the third law starts with a German physical chemist named Walther Nernst. And Nernst is a fascinating character. Born in 1864 in what was then Prussia, he was brilliant, ambitious, and by many accounts, rather vain. He drove one of the first automobiles in Göttingen, which was quite the spectacle in the 1890s. He made a fortune from inventing an electric lamp, the Nernst lamp, which for a while competed with Edison's incandescent bulb. He was wealthy, well-connected, and scientifically prolific. He also had a habit of annoying his colleagues. Einstein, who generally liked Nernst, once described him as a man who found his own ideas so important that he could barely contain his excitement about them. But Nernst's great contribution to thermodynamics came around 1906, when he was working on a practical problem in chemistry. Here's the issue. Chemists wanted to predict whether a chemical reaction would happen spontaneously. They knew that two things mattered: the energy change and the entropy change. A quantity called the Gibbs free energy combines both of these, and if the free energy decreases during a reaction, the reaction will proceed spontaneously. But to calculate the entropy part, you needed to know the absolute entropy of the substances involved, and that was a problem. Thermodynamics as it existed could only tell you about changes in entropy, not about absolute values. It was like knowing how much your bank balance changed without knowing what it started at. Nernst proposed what he called his heat theorem, which we now call the third law of thermodynamics. In its simplest form, it says that as the temperature of a system approaches absolute zero, its entropy approaches a minimum value. For a perfect crystal, a perfectly ordered arrangement of atoms, that minimum value is zero. Zero entropy at zero temperature. Think about what that means in terms of Boltzmann's formula. If S equals K log W and S equals 0, then W equals 1. There's only one microstate, At absolute zero, a perfect crystal has exactly one way to arrange itself. Every atom is locked into its place. There's no randomness, no uncertainty, no thermal jiggling. Everything is perfectly ordered. It's the most organized state imaginable. Now here's a practical consequence that's kind of wild. The third law implies that you can never actually reach absolute zero. You can get close, incredibly, astonishingly close, but you can never quite get there. Each step of cooling requires removing entropy from the system, and as you get closer and closer to zero, each step becomes harder and harder, requiring more and more effort for less and less cooling. It's an asymptotic approach. You can spend infinite effort and still not quite arrive. And this isn't just theoretical hand-waving. Experimentalists have pushed temperatures down to billionths of a degree above absolute zero. In laboratories around the world, physicists routinely work at temperatures colder than outer space. The cosmic microwave background radiation, the afterglow of the Big Bang, sits at about 2.7 Kelvin. Modern cryogenics labs can reach nano-Kelvin temperatures, a billion times colder than that. But zero itself remains forever out of reach. Nernst received the Nobel Prize in Chemistry in 1920, primarily for his heat theorem. And the third law, once established, gave chemists exactly what they needed: a reference point for entropy. You could now calculate the absolute entropy of any substance by measuring its heat capacity from as close to absolute zero as you could get up to whatever temperature you cared about. You integrate the heat capacity divided by temperature, starting from zero, where the entropy is zero, and you get the absolute entropy. This was enormously useful for predicting chemical reactions, for understanding phase transitions, for all sorts of practical chemistry and engineering. So now we have all three laws. Or rather, all four laws, because there's actually a zeroth law that we should mention, since it's so fundamental that it was named retroactively. The zeroth law was formalized in the 1930s by Ralph Fowler, though the concept was implicit in everything that came before. It says simply this: if System A is in thermal equilibrium with System C, and System B is also in thermal equilibrium with System C, then A and B are in thermal equilibrium with each other. That sounds almost trivially obvious, right? But it's actually the thing that makes temperature a meaningful, well-defined concept. It's what justifies using a thermometer. When you stick a thermometer in your coffee, you're relying on the zeroth law. The thermometer reaches equilibrium with the coffee, and because you trust the zeroth law, you know the temperature reading applies to the coffee itself. It was called the zeroth law because it's logically prior to the first and second laws. They all assume temperature is a coherent concept. But historically, it was recognized last. There's a wonderful way to summarize all four laws that gets passed around in physics and engineering circles. You might have heard some version of it. The zeroth law says, there is a game. The first law says, you can't win. You can only break even. The second law says, you can only break even at absolute zero. The third law says, you can never reach absolute zero. So you can't win, you can't break even, and you can't quit the game. It's a little grim maybe, but it captures something true about the constraints the universe imposes on everything we try to do. And those constraints are what make engineering so interesting, because engineering is fundamentally the art of working within limits. Every power plant, every refrigerator, every rocket engine, every air conditioner is a machine designed by people who understood these laws and figured out how to get as close to the theoretical limits as possible without crossing them. because you can't cross them. The laws of thermodynamics aren't suggestions. They're not guidelines. They're the hardest walls in the universe. Let's talk about how engineers have pushed against those walls, because that story takes us into the age of industrial thermodynamics, the era when understanding these laws wasn't just an intellectual exercise, but a matter of enormous economic and strategic importance. And one of the best places to see that story unfold is in the development of the steam turbine, which transformed the second half of the 19th century in ways that the reciprocating steam engine, for all its importance, never could. The man at the center of this story is Charles Parsons, and if you've never heard of him, that's a shame, because what he built changed the world. Parsons was born in 1854 in London, the youngest son of the Earl of Rosse, who was himself an astronomer famous for building the largest telescope of the 19th century. So Parsons grew up in a household where engineering and science weren't abstract. They were things you did with your hands, things you built in workshops. He studied at Cambridge, apprenticed in engineering firms, and by his early 30s, he had an idea that would make reciprocating steam engines look like antiques. The problem with piston-based steam engines, even the best ones, was that the back-and-forth motion of the piston was inherently inefficient for generating electricity. What you really wanted was smooth, continuous rotary motion. And Parsons realized that if you could get steam to push against a series of carefully shaped blades mounted on a spinning shaft, a turbine, you could extract energy from the steam far more smoothly and efficiently than any piston could manage. The trick was that you couldn't just blast steam at a single set of blades. The steam would lose some energy, slow down a little, and then what? Parsons's insight was to use multiple stages. The steam would pass through one ring of moving blades, then through a ring of fixed blades that redirected it, then through another ring of moving blades, and so on. Each stage extracted a little more energy. The steam expanded and cooled gradually through the turbine, and by the time it came out the other end, you'd captured as much of its energy as thermodynamics would allow. In 1884, Parsons built his first steam turbine and coupled it directly to an electrical generator. It produced about 7.5 kilowatts, modest by today's standards, but the principle was proven. And here's where Parsons did something that engineers love and that shows real confidence in your own work. In 1897, at the Spithead Naval Review, a grand display of the Royal Navy's fleet in honor of Queen Victoria's Diamond Jubilee, Parsons showed up uninvited in a small vessel called the Turbinia. This boat was powered by his steam turbines, and while the Navy's finest warships sat at anchor, looking impressive, Parsons opened the throttle and sent the Turbinia screaming through the assembled fleet at over 34 knots. That was faster than anything the Royal Navy had. The patrol boats sent to intercept him couldn't keep up. It was part demonstration, part stunt, and entirely effective. The Admiralty was convinced, and within a few years, turbine propulsion became standard for warships, and eventually for the great ocean liners too. The Lusitania and the Mauretania, those famous Cunard liners launched in 1907, both ran on Parsons' steam turbines. The Mauretania held the Blue Riband, the unofficial prize for fastest Atlantic crossing, for over 20 years. And all of that speed, all of that power, came down to the same thermodynamic principles Carnot had sketched out on paper back in 1824. You take heat from a hot source, you convert some of it into work, and you reject the rest to a cold sink. The turbine was just a spectacularly elegant way of doing the converting part. But here's the thing about turbines that connects back to something we talked about much earlier. Carnot's efficiency limit. Remember, Carnot showed that the maximum efficiency of any heat engine depends on the temperature difference between the hot source and the cold sink. The bigger that difference, the more work you can squeeze out. So if you want a more efficient turbine, you have two basic options. You can make your cold sink colder, which is hard because your cold sink is usually the ocean or a river or the atmosphere, and you can't really change those. Or you can make your hot source hotter. And that's exactly what engineers spent the next century trying to do. This is where thermodynamics stops being abstract theory and becomes an incredibly practical materials science problem. Because making steam hotter means higher pressures, and higher pressures mean your boilers and your turbine blades and your pipes all need to withstand enormous forces at extreme temperatures. Steel behaves differently when it's glowing red. Metals creep, and creep is a real engineering term, not just a metaphor. At high temperatures, metal slowly deforms under stress, even stress well below what would break it at room temperature. It stretches, it sags, it eventually fails. So pushing for higher temperatures meant developing new alloys, new manufacturing techniques, new ways of understanding how materials behave when you push them toward their limits. In the early 1900s, power plants ran steam at maybe 300 degrees Celsius and modest pressures. By the 1950s, engineers were pushing toward 540 degrees Celsius and pressures above 200 atmospheres. That's 200 times atmospheric pressure. Think about what that means for the steel containing that steam. Every weld, every joint, every bolt has to hold against forces that would love nothing more than to blow the whole thing apart. And the thermodynamic payoff was real. Efficiency climbed from maybe 15 or 20% in the early days to over 40% in the best modern plants. 40% might not sound spectacular, but remember Carnot's lesson. There's a hard ceiling, and getting closer to it gets exponentially harder. Every additional percentage point of efficiency in a large power plant can save millions of dollars in fuel costs per year and prevent thousands of tons of carbon dioxide from entering the atmosphere. And this is where the story of thermodynamics intersects with something you experience every single day without thinking about it. When you flip a light switch or charge your phone or run your air conditioning, there's a very good chance that the electricity flowing to you was generated by a steam turbine somewhere. Even today, in the 21st century, the majority of the world's electricity comes from steam turbines. Coal plants, natural gas plants, nuclear plants, they all, at their core, do the same thing. They heat water, they make steam, they spin a turbine, and that turbine spins a generator. The heat source varies, burning coal, burning gas, splitting uranium atoms. But the thermodynamic cycle is recognizably the same one Carnot described 2 centuries ago. Even many solar thermal plants work this way. They use mirrors to concentrate sunlight, heat a fluid, make steam, spin a turbine. It's Carnot all the way down. Now, there's a particular kind of power plant that deserves some attention here, because it represents one of the cleverest thermodynamic tricks engineers have pulled off, and that's the combined cycle gas turbine plant. Let me walk you through this because it's genuinely elegant. In a simple gas turbine, basically a jet engine bolted to the ground, you burn natural gas, and the hot combustion gases spin a turbine directly. No steam involved. The exhaust comes out hot, maybe 500 or 600 degrees Celsius. In an old-fashioned, simple cycle plant, that hot exhaust just goes up the stack and into the atmosphere. And that's wasted heat. That's energy you paid for in fuel that's just warming the sky. Thermodynamically, it's leaving money on the table. So what engineers figured out, starting seriously in the 1960s and 70s, was to take that hot exhaust gas and route it through a heat recovery steam generator, essentially a big boiler. The exhaust heats water, makes steam, and that steam drives a second turbine, a steam turbine. So you're running two thermodynamic cycles, one on top of the other. The gas turbine cycle operates at very high temperatures. The combustion gases can be over 1,300 degrees Celsius at the turbine inlet and rejects its waste heat at 500 or 600 degrees. Then, the steam cycle picks up that waste heat as its hot source and rejects heat at maybe 30 or 40 degrees down to the cooling water. The combined effect is remarkable. Modern combined cycle plants achieve thermal efficiencies above 60%. 60%. Carnot would have been amazed, not because they've broken any laws, they haven't, but because they've gotten so close to the theoretical maximum by cleverly stacking cycles. And this gets to something beautiful about the second law. It doesn't just tell you what you can't do. It tells you where the losses are. It gives you a map of where energy is being wasted, where entropy is being generated unnecessarily, and therefore where a clever engineer might find room to improve. There's actually a formal framework for this called exergy analysis, sometimes called availability analysis. The idea is that not all energy is created equal. A joule of energy in the form of high-temperature, high-pressure steam is worth more, in terms of its ability to do useful work, than a joule of energy in lukewarm water. Exergy is a measure of how much useful work you can theoretically extract from a given amount of energy relative to the environment around you. And when you do an exergy analysis of a power plant or a chemical process or a refrigeration system, you can pinpoint exactly where the biggest thermodynamic losses are happening. Maybe it's in the combustion process itself, where the chemical energy of the fuel gets converted to heat, with a big entropy increase. Maybe it's in a heat exchanger, where there's too large a temperature difference between the two fluids. Every irreversibility, every departure from the ideal reversible process Carnot imagined, shows up as exergy destruction. And that destruction is permanent. You can't get it back. The entropy has been created, the universe has moved a little further from equilibrium, and that's that. This way of thinking, tracking not just energy but the quality of energy, has become essential in modern engineering. It's how engineers design more efficient jet engines, more effective chemical plants, better refrigeration systems. And it all traces back to Clausius sitting in his study, trying to make mathematical sense of why heat flows the way it does. Speaking of refrigeration, let's talk about that for a moment, because it's another place where thermodynamics shaped the modern world in ways most people never think about. The basic idea of a refrigerator is that you're running a heat engine in reverse. Instead of taking heat from a hot place and converting some to work, while dumping the rest somewhere cold, you're using work to move heat from a cold place to a hot place. You're pumping heat uphill against its natural tendency to flow from hot to cold. The second law says heat won't flow from cold to hot on its own, but it doesn't say you can't make it happen. You just have to pay for it with work. The first practical refrigeration systems appeared in the mid-1800s. James Harrison, a Scottish-born Australian, built commercial ice-making machines in the 1850s using ether compression. Carl von Linde in Germany developed ammonia-based refrigeration in the 1870s that became the foundation for industrial cooling. And these machines transformed entire industries. Brewing, meatpacking, food distribution, all of them were revolutionized by the ability to control temperature. Before mechanical refrigeration, if you wanted to keep food cold, you needed natural ice, cut from frozen lakes in winter and stored in insulated ice houses. The ice trade was a real industry. Frederick Tudor, the so-called Ice King of Boston, made a fortune in the early 1800s shipping ice from New England ponds to the Caribbean, to India, to anywhere people would pay for cold. It's a wild story in its own right. Tudor went bankrupt multiple times before making it work, and the idea of shipping ice across the tropics seemed insane to most people. But the demand was there, because humans crave cold drinks and fresh food, and thermodynamics was the barrier. Mechanical refrigeration demolished that barrier. And the thermodynamic cycle at the heart of your kitchen refrigerator right now, the vapor compression cycle, is something worth understanding, because it's beautifully simple in concept. You have a fluid, a refrigerant, that circulates in a closed loop. A compressor squeezes the refrigerant, raising its pressure and temperature. The hot, high-pressure refrigerant flows through coils on the back or bottom of your fridge. Those warm coils you can feel if you reach behind it. And it dumps heat into your kitchen. As it loses heat, it condenses from a gas into a liquid. Then the liquid passes through a tiny restriction, an expansion valve, and its pressure drops suddenly. When the pressure drops, the refrigerant cools dramatically. This is the same principle that makes a can of compressed air feel cold when you spray it. The cold, low-pressure refrigerant then flows through coils inside the fridge, absorbing heat from the food and the air inside. It warms up and evaporates back into a gas. Then the compressor grabs it again, and the cycle repeats. Heat is being moved from inside the fridge, the cold place, to your kitchen, the warm place. And the compressor is doing the work to make it happen. The electricity powering that compressor is the price you pay to move heat in the wrong direction, thermodynamically speaking. And the efficiency of this process, just like with heat engines, has a theoretical maximum set by the temperatures involved. It's called the coefficient of performance, and it's the refrigeration equivalent of Carnot efficiency. The closer the inside temperature and the outside temperature are to each other, the less work you need to do. Which is why your fridge doesn't have to work nearly as hard as your freezer, and why air conditioning in Phoenix, Arizona, on a 115-degree day is so brutally expensive in energy terms. The second law is right there in your electricity bill, quietly enforcing its rules. Now, there's another thread of this story that we haven't really touched yet, and it connects thermodynamics to something that might seem completely unrelated at first: the fate of the entire universe. Because once you accept that entropy in a closed system always increases, once you accept that energy tends to spread out and become less available for doing work, then you have to ask a very uncomfortable question. What happens when all the entropy that can increase has increased? What happens when every temperature gradient has flattened out, every concentration has diffused, every bit of usable energy has been converted into waste heat, spread so thin and so evenly across the cosmos that nothing can ever happen again? This idea has a name. It's called the heat death of the universe, and it's one of those concepts that sounds like science fiction, but it comes straight out of the second law of thermodynamics, taken to its logical, cosmic conclusion. The person who first articulated it clearly was William Thomson, Lord Kelvin, the same man who helped formalize the second law in the first place. In 1852, just a couple of years after his initial work on thermodynamic principles, Thomson published a short paper called On a Universal Tendency in Nature to the Dissipation of Mechanical Energy. and the title alone tells you where he was headed. He argued that the universe is winding down, that mechanical energy is constantly being converted into heat, and that heat is constantly spreading out, becoming more uniform, becoming less useful. And this process, he said, is irreversible. You can't undissipate energy. You can't unspread heat. The second law doesn't have an undo button. Think about what that means on the scale of everything. Stars burn fuel and radiate light and heat into space. That radiation spreads outward, gets absorbed, gets re-radiated, gets diluted across ever larger volumes. The fuel inside stars gets used up. New stars form from collapsing gas clouds, sure, but those clouds themselves were enriched by older, dead stars. Each generation of stars converts a little more nuclear binding energy into thermal radiation. Each cycle, the universe gets a little closer to a state where all the energy is still there. Energy is conserved. The first law guarantees that. But none of it is available to do anything useful. The entropy of the universe keeps climbing, and there's no ceiling, no point where it reverses. It just keeps going. Thomson imagined a future, impossibly far in the future, trillions upon trillions of years from now, where the universe reaches thermodynamic equilibrium. Every point in space is the same temperature. There are no gradients, no flows, no engines that can run, no stars that can shine. Everything is a uniform, lukewarm bath of radiation. And in that state, nothing happens. Nothing can happen. Not because the laws of physics have changed, but because there's no free energy left to drive any process. It's the most profound kind of stillness imaginable. Now, here's the thing. This idea shook people when Thomson proposed it. It wasn't just a physics result. It felt existential. It felt theological. If the universe is running down, if everything is heading toward this cold, featureless equilibrium, then what's the point? Victorian society took this very seriously. Writers, philosophers, theologians, they all grappled with it. The poet and philosopher Bertrand Russell, decades later, would write about the firm foundation of unyielding despair that the heat death implied. It was the first time a law of physics had something genuinely unsettling to say about the meaning of existence. And yet, here we are, billions of years into the universe's history, and things are clearly not in equilibrium yet. Stars are still burning. Galaxies are still forming. Life exists. You exist. You're lying here right now, a beautifully complex, low-entropy structure, maintained by a constant flow of energy from the sun, through the biosphere, through your food, through your metabolism, and out as waste heat radiated into the cold of space. You are a temporary, local violation of the trend toward disorder. Not a real violation, because you're not a closed system. You eat, you breathe, you radiate heat. You maintain your internal order by increasing the entropy of your surroundings. The second law is satisfied. But you get to exist in this beautiful, ordered state for a while, and that's something. This is actually one of the most profound insights to come out of thermodynamics, and it was developed most clearly in the 20th century by physicists like Erwin Schrödinger. Yes, the same Schrödinger with the cat. In 1944, Schrödinger published a little book called What is Life? And in it, he asked a question that seems almost naive, but turns out to be incredibly deep. How do living organisms maintain their highly ordered structure in a universe that's constantly trending toward disorder? His answer was elegant. Living things, he said, feed on negative entropy, or negentropy. as he called it. They take in low entropy energy in the form of structured, organized molecules like sugars and fats, and they export high entropy waste, carbon dioxide, water vapor, heat. The net entropy of the organism plus its environment goes up, just as the second law demands. But the organism itself stays ordered. It stays alive. It's like a whirlpool in a river. The water is always flowing downhill, always increasing in entropy. But the whirlpool maintains its structure as long as the flow continues. Cut off the flow, and the whirlpool disappears. Cut off the food and oxygen, and the organism dies, and its structure decays, and its entropy increases rapidly. Decomposition is just the second law catching up. This connection between thermodynamics and biology opened up entire new ways of thinking about life. It influenced the development of molecular biology, of information theory applied to genetics, of our understanding of ecosystems as energy processing systems. And it all traces back to Clausius's entropy, to Boltzmann's statistical interpretation, to this idea that the universe has a direction, a tendency, an arrow. And that phrase, the arrow of time, is worth sitting with for a moment. Because here's something genuinely strange about the laws of physics. Almost all of them are time reversible. Newton's laws of motion work perfectly well if you run time backward. Maxwell's equations of electromagnetism don't care which direction time flows. Even quantum mechanics, at its most fundamental level, is symmetric in time. If you filmed a simple interaction between particles and played the film backward, the physics would look perfectly valid. There's nothing in those fundamental laws that says time has to go in one direction. But the second law of thermodynamics does. Entropy increases toward the future. It doesn't increase toward the past. That's the asymmetry. That's what gives time its direction, at least from a physical perspective. The reason you remember yesterday but not tomorrow. The reason eggs break but don't unbreak. The reason you age, all of this, at some deep level, traces back to the second law. The arrow of time is an entropy arrow. Now, this raises a genuinely hard question that physicists have argued about for over a century. Why was the entropy of the universe so low in the first place? If the natural tendency is for entropy to be high, if high entropy states are overwhelmingly more probable than low entropy states, and Boltzmann showed us that they are, then why did the universe begin in such an extraordinarily low entropy state? The Big Bang was hot and dense, but it was also remarkably uniform, remarkably ordered in a gravitational sense, and all the complexity we see around us, galaxies, stars, planets, oceans, forests, cities, all of it is powered by the gradual unwinding of that initial low entropy. We're still coasting on the thermodynamic gift of the Big Bang. This is sometimes called the past hypothesis, the idea that the initial conditions of the universe were very special, very low in entropy, and that everything since has been a long, slow slide toward equilibrium. Some physicists, like Roger Penrose, have tried to quantify just how special those initial conditions were, and the numbers are staggering. Penrose estimated that the probability of the universe starting in such a low entropy state by chance is something like 1 in 10 to the power of 10 to the power of 123. That's not a number you can write down. That's not a number that has any intuitive meaning. It's just incomprehensibly unlikely. And yet, here we are. Nobody has a fully satisfying answer for why the initial entropy was so low. It might have something to do with the nature of gravity and how it behaves differently from other forms of entropy. In most systems, high entropy means things are spread out and uniform. like gas filling a room evenly. But with gravity, high entropy means things are clumped together, matter collapsed into black holes. So the early universe, which was very uniform, was actually in a very low entropy state gravitationally, even though it was very hot and seemed disordered in other ways. The gravitational entropy had enormous room to grow, and that growth is what drove the formation of galaxies, stars, and everything else. It's a subtle and beautiful point, and it shows you that entropy isn't always as simple as things get messier. Sometimes things get clumpier, and that's the entropy increasing. But let's bring this back down to Earth for a moment, because thermodynamics isn't just about the fate of the cosmos. It's about the world you live in every day. And one of the most pressing ways that the laws of thermodynamics shape your daily life right now, today, is through the question of energy and climate. Because here's the uncomfortable truth that the second law forces us to confront. There is no such thing as a perfectly efficient energy conversion. Every power plant, every engine, every industrial process generates waste heat. Every time we burn fossil fuels to generate electricity, we're converting chemical energy into thermal energy, then into mechanical energy, then into electrical energy. And at every step, some fraction is lost as unusable heat. Even the best combined cycle gas turbine plants we talked about earlier, the ones pushing 60% efficiency, that still means 40% of the energy in the fuel becomes waste heat dumped into the environment. And for older coal plants, the number is worse. 60 or 65% of the energy goes up the cooling tower as waste heat. This isn't an engineering failure. It's a thermodynamic reality. Carnot told us this almost 200 years ago. You cannot convert heat into work with perfect efficiency. The second law forbids it. And so, as long as our civilization runs on thermal processes, burning things to make heat to make work, we are fundamentally, inescapably limited in how efficiently we can use energy. And the waste heat we produce contributes, in its own small way, to warming the planet, on top of the greenhouse effect from the carbon dioxide we're releasing, which is part of why there's been so much interest in energy conversion methods that sidestep the thermal bottleneck entirely. Solar photovoltaic cells, for instance, convert light directly into electricity without ever going through a heat engine cycle. They're not bound by Carnot efficiency in the same way. They have their own theoretical limits. The Shockley-Kieser limit for a single junction cell is about 33%. But those limits come from quantum mechanics and the solar spectrum, not from the second law's constraint on heat engines. Fuel cells convert chemical energy directly into electrical energy through electrochemical reactions, again bypassing the thermal step. These technologies don't escape thermodynamics. Nothing does, but they engage with different aspects of it. And in some cases, that means higher practical efficiencies for specific tasks. And this brings us to something that engineers and physicists have been thinking about more and more in recent decades, something that ties together everything we've been talking about, from Carnot's ideal engine to Boltzmann's atoms to the entropy of the universe. It's the idea that thermodynamics isn't just about heat and work anymore. It's become a framework for thinking about information, complexity, and the fundamental limits of any physical process. And the person who perhaps did the most to push thermodynamics into this broader territory was a physicist working at IBM in the 1960s and 70s, a man named Rolf Landauer, who asked a question that sounds almost too simple to be interesting. What is the minimum amount of energy required to erase a single bit of information? Not to write it, not to read it, but to erase it, to take a bit that could be either a 0 or a 1 and reset it to a known state. And what Landauer figured out, in a paper published in 1961, was that this seemingly abstract question had a very concrete, very physical answer. Erasing a bit of information, just one bit, must dissipate at least a tiny specific amount of energy as heat. That amount is kT times the natural logarithm of 2, where K is Boltzmann's constant and T is the temperature of the environment. At room temperature, that works out to about 3 × 10 to the minus 21 joules. An almost unimaginably small number. But the point isn't the size of the number. The point is that it's not zero. Think about what that means. It means that computation, the physical act of processing information, is tied to thermodynamics at the most fundamental level. Not because of engineering limitations, not because our transistors aren't small enough or our wires have resistance, but because of the second law itself. When you erase information, you're reducing the entropy of the system that held that information. You're taking something uncertain, a bit that could be 0 or 1, and making it certain. And the second law says you can't reduce entropy in one place without increasing it somewhere else. So the entropy has to go somewhere, and it goes into the environment as heat. Landauer's principle, as it came to be called, draws a direct line from Clausius's entropy to the ones and zeros inside your laptop. And here's what's really beautiful about this. Remember how Boltzmann connected entropy to probability, to the number of microscopic arrangements consistent with a macroscopic state? And remember how Claude Shannon, working at Bell Labs, defined information entropy using essentially the same mathematical formula? Those parallels weren't just formal coincidences. Landauer showed that they reflect a deep physical reality. Information is physical. It's not some abstract, ethereal thing floating in the realm of pure mathematics. Information is always encoded in some physical system. Charges on a capacitor, magnetic domains on a disk, molecules in a cell, neurons in a brain. And manipulating that information is a physical process subject to physical laws, including the second law of thermodynamics. Now, Landauer wasn't working in a vacuum. Well, not a conceptual vacuum anyway. His thinking connected back to a puzzle that had been nagging physicists for over a century, one of the most famous thought experiments in all of physics, Maxwell's demon. James Clerk. Maxwell proposed it back in 1867, and we haven't really talked about it yet, so let's take a moment with it. Because it's one of those ideas that seems like a clever party trick at first, but turns out to touch something genuinely profound. Maxwell imagined a tiny, intelligent being, a demon, he called it, though he meant it playfully, sitting at a small door between two chambers of gas that are initially at the same temperature. The demon watches individual molecules approach the door. When a fast-moving molecule comes from the left, the demon opens the door and lets it through to the right. When a slow-moving molecule comes from the right, the demon opens the door and lets it through to the left. Over time, the right chamber fills with fast molecules. It gets hotter, and the left chamber fills with slow molecules. It gets cooler. The demon has separated hot from cold without doing any work. It seems to have decreased the entropy of the system, violating the second law, just by being clever about opening and closing a tiny door. For decades, this was genuinely troubling. People proposed various resolutions. Maybe the demon has to exert energy to operate the door. Maybe the act of observing the molecules requires work. But none of them were fully satisfying. It was the Hungarian physicist Leo Szilard who made the first really important step in 1929, arguing that the demon's act of measurement, of acquiring information about each molecule's speed, must itself have a thermodynamic cost. Szilard connected information to entropy in a way that foreshadowed both Shannon and Landauer, though his ideas weren't fully appreciated at the time. But it was Landauer, and then his colleague at IBM, Charles Bennett, in the early 1980s, who really nailed it. Bennett showed that the daemon can actually measure the molecules and sort them without necessarily paying an energy cost. Measurement itself can, in principle, be done reversibly. The real cost comes when the daemon's memory fills up. The daemon has to remember which molecules it let through and which it didn't. Eventually, it has to erase that memory to keep operating. And erasing information, as Landauer proved, has an unavoidable thermodynamic cost. That erasure generates exactly enough heat to compensate for the entropy decrease the daemon achieved. The books balance. The second law survives. This resolution is so elegant it almost makes you want to laugh. The daemon isn't defeated by mechanics or by the difficulty of being very small. It's defeated by the thermodynamics of forgetting. The act of clearing its notebook, so to speak, produces exactly the waste heat needed to preserve the second law. Information and entropy are not just analogous. They are the same coin viewed from different sides. And this has real engineering consequences today. Think about your phone, your computer, any digital device. Every time a transistor switches, every time a logic gate resets, every time data is overwritten, Landauer's principle sets a floor on the energy that must be dissipated. Now, in practice, modern computers operate far, far above that floor. Current transistors dissipate thousands of times more energy per operation than the Landauer limit requires. But as chips get smaller, as transistors shrink toward atomic scales, as engineers push for ever lower power consumption, that fundamental floor starts to matter more and more. It's the thermodynamic bedrock beneath all of computing. You cannot build a computer, no matter how advanced your technology, that uses less energy per irreversible operation than Landauer's limit. The second law won't let you, and this connects to something even broader that's been happening in physics over the last few decades, a kind of quiet revolution in how people think about thermodynamics itself. For most of its history, thermodynamics was a theory of equilibrium. It described systems that had settled down, reached a steady state, stopped changing, the steam in a cylinder at a uniform temperature and pressure, a block of ice in a warm room long after it's finished melting. But the real world is almost never in equilibrium. Life isn't in equilibrium. Weather isn't in equilibrium. A cell dividing, a hurricane forming, a brain thinking, these are all far from equilibrium processes, and classical thermodynamics had surprisingly little to say about them. That started to change in the mid-20th century with the work of Lars Onsager and Ilya Prigogine. Onsager, a Norwegian-born chemist working in the United States, developed a framework for understanding systems slightly out of equilibrium, what's called linear non-equilibrium thermodynamics, and won the Nobel Prize for it in 1968. Prigogine, a Russian-born Belgian, went further, exploring systems far from equilibrium and showing that they could spontaneously develop organized structures, what he called dissipative structures. Think of a hurricane, or the convection cells that form in a pot of water heated from below, or the beautiful hexagonal patterns called Bénard cells. These are systems that maintain their structure by continuously dissipating energy, by constantly producing entropy and exporting it to their surroundings. Prigogine won his Nobel in 1977, and his work hinted at something that Schrödinger had intuited decades earlier in What is Life? that living organisms might be understood as dissipative structures, maintaining their exquisite internal order by feeding on low entropy energy and excreting high entropy waste. And in the 21st century, this line of thinking has produced some genuinely startling results. In 2015, a young physicist at MIT named Jeremy England proposed a theoretical framework suggesting that matter, when driven by an external energy source and surrounded by a heat bath, will tend to self-organize in ways that maximize entropy production. Not that it must, but that there's a statistical tendency towards structures that are particularly good at dissipating energy. England was careful not to overclaim. He wasn't saying he'd explained the origin of life, but the implication was tantalizing. Maybe the emergence of complex, self-replicating structures isn't some unlikely accident that thermodynamics merely tolerates. Maybe it's something thermodynamics actively favors, because those structures are so effective at increasing the entropy of the universe. It's a speculative idea, and it's still being debated and tested. But just sit with it for a moment. The second law, this principle that seemed so grim to the Victorians, this law of universal decay and heat death, might actually be the very thing that drives the emergence of complexity, of life, of you lying here right now, listening to these words. Entropy isn't just the villain of the story. It might be the author, and that feels like a good place to start winding down. Because in a way, we've come full circle. We started with ancient people watching fire and wondering what heat was. We followed that wonder through the steam engines of Newcomen and Watt, through Carnot's brilliant abstraction of the ideal engine, through Joule's painstaking experiments with paddle wheels and thermometers, through Clausius giving entropy its name, and Boltzmann giving it a meaning in terms of atoms and probability. A meaning so controversial, it may have contributed to his tragic death. We watched Thomson predict the heat death of the universe, and Nernst establish the unattainability of absolute zero. We saw Parsons build a turbine that changed naval warfare and power generation forever. And we traced the long, patient work of engineers pushing thermal efficiency closer and closer to the limits that Carnot identified almost 2 centuries ago. And then we saw thermodynamics reach beyond heat and work, into information with Shannon and Landauer, into biology with Schrödinger and Prigogine, into cosmology with Penrose and the past hypothesis. These 4 laws, the zeroth, the first, the second, the third, they're not just rules about steam engines. They're among the deepest statements we've ever made about how the universe works. They tell us that temperature is real and measurable, that energy is conserved, that entropy tends to increase, and that absolute zero can never quite be reached. Simple enough to state in a sentence each, profound enough to occupy the greatest minds for centuries. And here's maybe the most comforting thought to end on. You, right now, are a thermodynamic marvel. Your body maintains itself at about 37 degrees Celsius, a warm island of low entropy in a cooling universe. You take in low entropy energy, the organized chemical energy in food, and you radiate high entropy waste heat into the air around you. Every breath you take, every heartbeat, every fleeting thought drifting through your mind as you settle toward sleep. All of it is thermodynamics in action. The same laws that govern stars and steam engines and the fate of the cosmos are keeping you alive, right now, in this quiet moment. Carnot would have marveled at you, honestly. A heat engine of astonishing subtlety, maintaining your internal order not through rigid mechanical cycles, but through billions of interlocking chemical reactions, each one nudging entropy along, each one contributing its tiny share of waste heat to the universe's great accounting ledger. And Boltzmann Boltzmann would have seen you as a spectacular fluctuation, an arrangement of atoms so improbable and so beautiful that it borders on the miraculous, sustained not by defying the second law, but by working with it, by riding the great entropic current like a leaf on a river. So as you lie here, warm and quiet, letting your thoughts soften and slow, know that you are participating in the deepest process the universe knows. Entropy is rising, as it always does, as it always must. But along the way, it builds things like you, complex, conscious, curious enough to wonder how it all works, and that, when you think about it, is not a bad deal at all. The universe is winding down, yes, slowly, over timescales so vast they make human history look like a single heartbeat. But in the meantime, in this brief, bright interval between the low entropy beginning and the high entropy end, there is warmth and complexity and life and the quiet pleasure of understanding, even just a little, the laws that make it all possible. That's enough. That's more than enough. Let that thought settle over you like a blanket, and let the second law carry you gently, as it carries everything, toward rest.